We have a question here, and it states that we have a source here. We have 5 ohm resistor here, a capacitor, and an inductor. And we are given the resistance of the capacitor and inductor. Okay. So capacitance and inductance is going to create reactance. So we'll denote it as in the J form. And we know that capacitance, since it doesn't resist current, right? It allows current to flow. But inductance resists current. An inductor will make voltage lead. So it'll be 3J. This will be negative 2J. And it is negative because it makes current lead. And since current is leading, it makes the sign negative, right? So since we have those values, we're going to then, the question states, specifically this question, all the work, ignore the work. You know what I'm saying? Let me actually scribble out all the work. All right, the question states that we're given those values, but what is the power factor, right? We're not given the voltage source, but we are given all the resistance values in the circuit. So since we're given that, we can determine the power factor. Why is this dying? First, we'll combine this capacitor and inductor like you normally do, right? 1 over 3J, right? You're going to combine those. Okay. So cross multiply, we'll get 3J times negative 2J over negative 2J plus 3J. And J squared, we'll make it negative, negative. We'll get 6 up top, divided by negative 2J plus 3J is just J. So times J on the bottom and the top to get rid of it. We'll get 6J, and J squared on the bottom makes a negative 1, so we'll get negative 6J. Okay, and then we're going to combine it with our 1 resistor, so we'll get 5 minus 6J, and this will be Z total, right? Okay. So we have the total resistance. Now, how do we determine the power factor? The power factor is the difference between the phase angle of the voltage and the current. And something we know about from Ohm's law, right? Let's look at this, but instead of this equation, let's look at strictly at their angle, phase angle. So if we take the phase angle of the voltage, right, and divide it by the phase angle of the current, right, we get the angle of the voltage minus the current is equal to R. So R directly relates to the difference in their angles if we know the phase angle of the impedance. So if you want to find the power factor, one way you can find it is by knowing Z total. The phase angle of Z total will give you the phase angle you need for the power factor. And the power factor is going to be the cosine of the V angle, or the phase angle of the voltage, minus the phase angle of the current, right? Or the phase angle of the resistance. So to find the phase angle of this resistance, we'll take negative 6, the imaginary, divided by the real. Take the inverse tangent of that. And that's how you get the phase angle of any complex rectangular form number. And you should get, we're going to get this value, negative 50.2 is going to be the angle. So we're going to plug that in the cosine. Cosine of negative 50. Make sure your calculator is in degrees for this. Cosine of negative 50.2. And we get 0.64. power factor is equal to 0.64. Lovely. And that's going to be the right answer. If we erase this and unveil what the answer is, we'll get, that's the wrong one. Undo that. For this one, we'll get 0.64. That checks out. Now let's move on to number 2. So for number 2, we have a voltage source of 100, a magnitude of 120 with a phase angle 30. And we have a resistor. And we have a capacitor. The circuit has a frequency of 60 Hertz. Compute the following: the source current and the real power provided by the source. Okay. Let's draw this circuit first. So we have this new circuit, right? And we have the source, the resistor, and the capacitor. The resistor is 3 ohms. The capacitance is given to us as 1 microfarad, right? C is equal to 1 microfarad. Micro or milli? No, it's not micro, it's milli. 1 milli? Oh yeah, millifarad. 1 millifarad. It's usually micro. Odd. Anyhow, and the frequency is 60 Hertz. So, how do we plug in how do we find the resistance at the capacitor? We're given Hertz, so how do we plug that in? Well, generally this is the form of a capacitor, right? The resistance. And to find omega W is equal to 2 pi f. F being the frequency, which we know is 60. And we know the capacitance, so we'll plug in those values to find our answer. And if you do that, we'll get negative 2.65 J, since it is a reactance component, is what I call it. Since these are in parallel, we'll combine them like they're in parallel, so we'll get 1 over 3 plus 1 over negative 2.65 J. Cross multiply. Okay, you could also put this in your calculator if it has complex numbers and get an easier answer. And if you want to simplify this further by hand, you can put it in phasor form, which we're going to get, let's see, let me simplify it. If you're doing the math or putting in your calculator, you should get this value is equal to Z total. Okay. Well, the question wants us to figure out the source current coming from the source and the real power provided by the source. Well, let's see. Well, we know that if we take voltage and divide it by R, we'll get current. So if we convert this to phasor form and then combine that, or divide that into voltage, we should get our answer. So negative 1.49 divided by 1.314, inverse tangent of that should get us our angle. Oh, I did it up here. I didn't have to do all that. I didn't realize. Okay, so we take 120, 30, and divide it by 1.9875 with an angle of negative 48.6. We should get our answer. 1.9875. Our magnitude's going to be, that's an angle of 78.6. Okay. Let's see how that checks out. And that is the right answer. I checked it. Trust. So we did good. Did good math. Alright, so now we need to figure out, let's see, the real power. It wants the real power provided by the source. Okay. Alright. So if we want to find the real power, we need this formula. V RMS times I RMS is equal to the cosine of V angle minus I angle. Right? This is the power factor, right? And the power factor really determines what is going to be useful as power when the voltage and current are lagging. So we know that the angles of voltage is 30 minus the angle of current is 78.6, which should be our resistance value, which is negative 48.6, which it looks like it is. So the cosine of 48.6 and VRMS is 120, and how do we know that? Is because you see this symbol, V with a V with a line above it. That means the peak voltage, or the voltage root mean square. Since that's already in that form, we know that current will also be in the RMS form, root mean square. So we can just multiply them out, right? So we got 120 times 60.4. And that's going to give us 48.6. 4,793. Let's check that answer. And that is right. This is correct. Question 2 of the practice is done. Doing good. Now let's go to question 3. Okay, so we have question 3 is what we're looking at first. An AC source is feeding a load that consists of resistance and reactance in series. The voltage and current of the sources are as follows. Okay, so we have the voltage and the current, and we're given the, what is this called right here? Radians? That is in radians. So you have the function, I don't know if I want to call it that, but you have, I don't know what to call this part, but over here you have the phase angle usually, or the phase shift, which is an angle typically, but since it's not an angle, it is in radians. So to convert from 0.38 to radians, we do 0.38, no. To convert from radians to degrees is what I meant to say. Pi over 180. Multiply it by that and you'll get your answer. But first, let's see what we need to approach first. We need to figure out, for this question, determine the reactance of, is there anything else? No, there's not. Let me go back. So yeah, we need to figure out the reactance given voltage and the real resistance part. So let's draw the circuit real quick and go in further detail on what to do. Alright, so to solve this problem, we know voltage, peak voltage is 500. And to figure out the angle, because we kind of want to put this in phasor form, because if we do V divided by current, we get R. And we can find Z total that way, and then find the reactance. So we know that V is 500 and I is 100. Now let's find the angles associated with them. Now, you may be thinking, why are we ignoring the cosine and everything? Well, the angle, the magnitudes are here, associated with voltage, and here are the phase angles right here. They're in radians, but we'll convert that. And actually, the formula is 0.38 times 180 over pi. Anyhow, let's find those values on my calculator here. 1 second. And you should get those values when you convert it to degrees. So let's solve that. We'll get 5 with an angle of 21.77. We're dividing this. Minus negative 35.52. 57.29. Now let's convert this to rectangular. So 5 times the cosine of 57.29, we get 2.70. And then the sine of 57.29 times 5 plus 4.20j. And that matches our answer. 4.2 is the inductance, or reactance, right? This is reactance. Now, why does it say inductance? Because it's positive. Since it's a positive reactance, we get a voltage lead, and this makes it an inductance, since it's positive. All right, now let's do question 4. All right, so here's our voltage and current, and if we're trying to calculate the complex power, S being the complex power is equal to V times I RMS conjugate of I. So to grab the conjugate of I, we need to expand it to its rectangular form, and we get negative 0.66j. The conjugate would make it positive. The conjugate only affects the imaginary number and inverts its sign. J times 3 minus 4j. So we can go back to phasor if we want to now, which would make it 0.66 divided by 4.96. Inverse tangent of that. Mode, put it in degrees. Make sure you're in degrees. So we get 7.58. The magnitude won't change, so it's going to be 5. You would think. Let me see. 4.96 squared plus 0.66 squared square root. Yeah, it's 5. Okay. And then we're going to take this back into phasor. It's going to be 4 squared plus 3 squared. Square root it. And with an angle of negative 4 divided by 3, inverse tangent of that, negative 53.13. Okay. So now, let's see what we get once we do all this. Hope I'm right. I'll add those together. So negative 53.13 plus 7.58. Goodness. Negative 45.55. Let's convert this to rectangular to check some of our work. Cosine of negative 44.55 times 25. 17.5. And look right. Sine of negative 45.55 times 25. Negative 17.85j. My bad. My calculator was in radians, so all my things are off. Let me redo that. That's supposed to be our initial value. And we need to grab the conjugate of that. We'll make it 0.53 minus 2.11 J. Okay. And if we put that in our calculator, 3 minus 4I, and then we have 4.53. You should have complex calculator in your calculator. It makes it way easier. We get 5.15 minus 24.45, not I, but J. Okay. So if we were to graph this, right, it would be power, real power, was 5.15 watts. And the reactive power, which is negative 24.25 bar, which is voltage ampere reactance. I think that's what it stands for. And then you have S. Right? You can find the magnitude. Grab the hypotenuse, 5.15 squared plus 24.25 squared. Square root of that, we get 24.79 is equal to the magnitude of S. Okay, how does that check out with R here? No. Here we go. Okay. Like I said. Right on. Okay, so we have 5.15 watts. And then we have the volt ampere reactive, which is the reactive power, is negative 24.25. And then we have VA, which is the apparent power, which is 24.79. Okay. That is the complex power for that question. All right. So, let's do question 5. We have this problem. A load that has a leading power factor, that's 0.7, dissipates 2 kilowatts real power. And we know that the source is 220 volts RMS and has 60 hertz. How do we change the inductance component needed to correct the power factor to 0.9? Okay, so this is a pretty tough problem, but it's not as bad as you think. It's not too bad. So, we know that we have 2,000 real power plus some X amount of reactance, right? Reactive power, right? We know the real, but we don't know the reactive. If we knew the reactive, we'd be done. But we have the power factor. And how does the power factor relate to that? Well, we know that the power factor, or the cosine of 0.7, no, mode, degree, second quit. The inverse cosine of 0.7. Okay. So when you grab the cosine, we know the cosine of V, the angle of the voltage minus the angle of the current is equal to the power factor. Now, if we want to get that angle back, we need to grab the inverse of cosine on both sides. It'll get rid of the cosine, and we'll get that angle back. Is equal to this angle. This angle is also equal to the resistance angle, right? The angle of the resistance will have, the impedance, which is 45.57 degrees. And we should also note that when we look at the power triangle, this is the real portion, and the imaginary is here. We don't know what that is, but we know this angle here, right? We know the angle. That angle is 45.57. And how do we know that angle relates? Well, when you calculate the power, no. When you calculate power, right? Power, how come the angle, this angle works here? Well, when you calculate the complex power, we know that S, which is the complex power, is equal to voltage times I conjugate, right? Now, we know that when you have two angles multiplied, you add them. But when you grab the conjugate of I, that angle, it makes it a negative, which is the same as saying subtracting, and that is equal to the power factor angle. So we can plug that angle into here, and then we can figure out that the tangent of 45, because opposite x over 2000, right, is equal to the tangent of this angle, 45.57 times 2000. We get var is equal to 2040. And now we have the first value we need to solve this problem. So we have var for when 0.7, when the power factor is 0.7. Our goal is to find the difference in the reactive power, right? And if we find the difference, the change in the, call it Q1, Q1 can be 2040 minus Q2. The difference is equal to how much we can need to change our inductance to get it to 0.9, right? So that's how I think about it. So we have 2040. So let's find the other value. It's going to be the inverse cosine of 0.9. All right, we're going to take the tangent, that number, times 2000, and var, this is for 0.9, this is, no, point, whoops, 0.7, and this is for 0.9, this is equal to 968.6, and the difference between them is 1071, right? That is the reactance that we want. We need to bring the reactance, how do I say this? Let me say this differently. Since we know that 1071 bars is our change in Q, and how are we going to go back and change the inductance to get to what we want? So we know that V squared over, let's say, the XL, we're going to say the reactance portion, right? We know that power is broken into its reactive and real part. So this would be equal to the reactive value. We know that V squared over R, the resistance, is equal to power typically, but if we were to replace that and look at the reactive portion specifically, you would get this. We know that V is equal to 220. And let's flip that around. Alright, and we're going to get a value of is equal to, and we know that XL, the impedance of an inductor, is going to look like 2 pi, the frequency was 60, times the inductance, which correlates to omega L. Omega is 2 pi times the frequency, and then L is just the inductance. So we're going to divide 2 pi 60 over, and we get 1.119 equal to L. Or you could round and say 0.120. It'll be the same. It's close enough. That's number 5. We have a circuit shown below. The source impedance is 3 plus 4J. What is the load impedance in order to deliver the maximum amount of power to the load? Right, what is the real power in this case found in the load? Well, unlike our typical DC circuit, instead of typically what we usually do is set the resistance as equal, we know that Z by itself is equal to 3 plus 4J. But in order for it to be maximum, we have to do Z conjugate, which is 3 minus 4J. Okay. And why is that? Why is it the conjugate? Well, if we do the conjugate, look what happens. The reactance will cancel out, and that's how you get the maximum real power. That is what happens. So, let's combine our resistance. So we'll just be left with 6 is equal to Z total. And to find power, we do voltage squared divided by 6. Since it's real, we don't have to convert to root mean square even if we wanted to. Is that root mean square? Let me think. 120 divided by okay. Since this is only real power, right? And typically voltage is given in root mean square. We're going to do 120. 120 is the peak voltage, my bad, divided by root 2. is 84.85. This gives us the root mean square voltage. I was confused. Squared divided by 6 will give us 1200 watts. Real. That's what we want. That question's done. It's a pretty fast one. Pretty easy. Easier than a lot of things. Let me erase all the work. Alright, so if we want to compute the load impedance of a single phase, we need to figure out the magnitude of the impedance and the phase angle. Terrence? Anyways. Let's see. So we know that the power directly correlates to, complex power directly correlates to the power factor. Has the same angle, right? So we know that we take 9, that's hella thick, 9,000, and divide it by 3,000? Because this is 9,000, the real, imaginary. We want this angle, it would be the adjacent over the opposite. Toe is opposite. Excuse me. Toe is opposite over adjacent, so 3,000 divided by 9,000. And then grab the inverse tangent. That'll give you 18.43. That's your phase angle of your power factor, which directly relates to our impedance, right? So now we need to find the magnitude of that, and we know that R is equal to V times I. We don't know I, but we know I is equal to when we calculated S is equal to voltage times conjugate I. So let me think really quick. So we can find S. S will be the magnitude. Let's do a single phase. We'll do 3,000 squared plus 1,000 squared divided by the square root. Alright, so we get S is equal to 3,162. And if we directly look at magnitudes, right, we divide by 120. Now, not just any 120. This is going to be the voltage when we're looking at a single phase across the resistor. So we want to increase the magnitude by root 3 because we want to find the current as it goes from, what am I on? Whoa. Back it up. I'm a little confused. Hold on, me step back. second. Need to readjust. Okay. And since we're strictly looking at the magnitude, we don't have to worry about the conjugate because that includes the phase angle. Did not mean to do that. So we're going to get 120 times root 3. This divided by that. We'll get 15.21 amps. Alright, and if we're strictly looking at the magnitude, we're not worried about the angle. We know that to find this is the wrong relationship. This is equal to voltage R over I. So V over I is equal to R. So it's going to be 120 divided by 15.21. We get 7.889. Okay, so I forgot to include the root 3. Oh my god. Because we're looking at a single phase. Alright, we're looking at the resistor. So 3162 divided by 120 times root 3. We get 15.21, which is what we want. Sweet. Now let's go to question 8. Okay. We have a 3-phase load. And we have total power, real power delivered to the load is 48 kilowatts at a power factor of 0.8, leading when the line voltage is 460 volts. Determine the load as a series combination of resistance and reactance. Okay, so there's resistance and reactance in each part of this Y connected load. Load is a good word. Okay, so the line to line is 460. Right, let me erase this work and start. Alright, so we know that 48,000, right, of real power. And we know the angle here is going to be inverse cosine of 0.8, which is 36.87 degrees. Alright, so we know that if we take tangent of that angle, we're just doing this to solve the rest of the variables, and get opposite over adjacent times 48,000. The reactive power is going to be 36,000 VARs. We know that if we take the the Pythagorean theorem, 48,000 squared plus 36,000 squared. Well, if we take the square root of that number, we'll get 60,000. This is equal to the apparent power, or we call it S, the magnitude. Okay, so we know that S is also equal to voltage times current conjugate. Okay. All right. So we need to determine the load as a series. So we need to find the impedance at a single load. Okay, so we know the line-to-line voltage is 460. All right. And if we want to look at a single load, we want to limit ourselves to, let's say, I don't know, if we're going from line to line to phase voltage, the voltage across a single load, we want to go and decrease 460 by a factor of 3. Now, a nice little trick to know whether you're increasing by a factor of 3, root 3, or dividing by root 3 is if you take the voltage from point A to B, the voltage from just by visualizing, you can kind of see that you need to decrease your factor since you're now narrowing your range from A to B, but now from A to neutral. So it's just kind of, you can kind of do that when you're converting from line to line or from when you're converting line to line to phase. When you either have phase delta or Y configurations, you can kind of visually see whether you need to increase or decrease. And it's always going to be root 3 for current and voltage. So since we're decreasing by 460 divided by, okay, and we're specifically focused on the magnitude because we know that with a power factor of 0.8, we know that the angle is going to be 36.87 for the impedance as well. That's going to be its phase angle. And how we know that is because the power factor, that angle is going to be the same for the voltage angle minus the current angle, which is equal to the impedance angle. Okay, so 265 volts. We're not going to focus on the phase angle of everything, so we want to figure out the current so we can then find the impedance later on. So we know if we take, what's the apparent power? 60,000 divided by 265, right? So we're going to get don't forget to divide. Oops. Don't forget to divide this by 3 because this is the apparent power across each load. So we need 20,000 divided by 265. That's going to give us 75.47 amps. And we know that if voltage divided by current is equal to Z, or we call it resistance for DC, but with the impedance, if we take 265 divided by 75.47, we get a good whopping 3.52. So our answer for the impedance across a single one is going to be 3.52 with a phase angle of 36.87. For his answer, you got a negative. I don't really know how you get a negative angle since cosine gives cosine of inverse cosine of 0.8 is going to be positive. But yeah, that is your answer from my point of view. His answer is going to have a negative 36.87. I don't see how you get that because inverse cosine of 0.8 is positive 36.87. So let's go to question 9 now, which states, I'm going to erase. Okay. So we're given two things. the load, the phase voltage at of the load, and the line current. Okay. So why am I acting slow? Okay, so we have voltage across the load, A to B. Okay, so VAB, or phase voltage across the load, is 100 with a phase of 0. Okay, and then we have line. The current at line B is 3 with an angle of negative 80 amps. Okay, since we're looking at AB, we kind of want to look at that. All right, so since we're at B, let's go back to line. We want line A if we're looking at VAB. Right? So that's going to give us, we can rotate this by a total of 120 degrees to go back up to A. It's going to be 40 amps. Okay. Now we want to know the total real power at the load. So to figure out the total real power at the load, okay, it's going to be, we're not looking at complex power, we're looking at the real power consumed at the load. I mean, we could look at complex power. Or do we? We do. So we're gonna solve this. Oops, that was my speaker. We're gonna solve this since we only want real power, right? We can do voltage times current times the cosine of the angle difference between voltage minus the current. And this cosine power factor will show us what the real power is, right? Instead of doing the other way, which is V times I conjugate, that'll show you both the real and reactive power. You can also do it with this one if you include all the angles and whatnot, but we're solely worried about the real power. So we know that IA is 3 with an angle of 40. And since we're looking at a single phase, we need to convert to phase. So we know that when we convert from line to phase for current, we see that we're just looking at IB for reference. When this current comes in, it breaks off into two different paths. So it's definitely going to be decreasing. So we are going to be dividing by root 3. Now, the phase, the angle is going to be different. Since this is a delta, we are going to be line current will lead phase current. So we're adding 30 degrees here. So IA will be equal to 3 over root 3 with an angle of 70. Or should I say, IAB. Or no, IAB. Something like that. The phase current. So we're going to multiply them together. Right? And multiply them by the power factor, and that's going to be cosine -70, right, times 100 times 3√3 3 divided by √3 times 100 times the power factor. Whoops. Did not mean to do that. Go back. What happened? I don't know what I did. Okay. This times the power factor of 0.34. Okay. I got 0.59. Not 0.59. 59. 59 watts. Okay. That's across a single phase, so the total real power is just going to be 59 times 3, which is approximately 180 watts. Cool. Alright, last problem. Let me white out this. You can see the real answer already, but I didn't actually look at it, so hopefully I can get it. Okay, in a three-phase circuit, the source is delta connected, but the load is Y connected. We know that phase voltage, phase A to N, of the load is 200 volts, and the line current is with a phase of 120. What is the power factor of the load? Okay, well, it's pretty straightforward. We have the phase voltage across one load, and we have the line current, C. So let's go to A. So we have phase A. We want phase current at A as well. If we have that, we can find the power factor at the load. And if we want to go take this IC current, line current, to phase A, we need to increase its angle, or decrease. I think decrease. Yeah. Minus, plus. Okay. Yeah, minus 120. So for will be line A, right? And now let's convert to phase current. Now, are we going to be increasing or decreasing? Well, the current, as it goes from neutral into the neutral, isn't increasing, but notice how the current that came out here, right? 1, 2, goes out to neutral. We know that if we look at the line current specifically, well, if we look, the line A goes straight to neutral, so there is no difference between the line current and the phase current. So this is equal to the phase current at the load, right? And we know that the phase voltage, VAN, at the load is 200 with an angle of 0 degrees. And the angle between the voltage and the current, is 0. So cosine of 0 is 1. Power factor is 1. Voila.